Okay. And I will also record these lectures. So if you are interested, you can look at the recorded video also. So first question I have to you. So we have 3 people joining online. So I decided to do these lectures in hybrid format so that you can come here and we can talk and you can ask questions more easily. But there are also 3 people who are now joining online. So the question here is maybe those who are joining on Zoom. Please put into the chat if you prefer to continue online or you prefer to come to the lecture room. And also you, so what is your opinion? So do you want to come here every day or do you want to keep this hybrid format so that you can sometimes listen maybe online also? So which you prefer? Who wants in person? Time and day. Nobody wants in person. So online. 2 online, the others don't care. Okay. Then we continue with hybrid. So maybe somebody sometimes wants to be online. Okay. For me, that's okay. I just have to carry cameras and such. So lecture dates are written here. So we are here at April 8th. Then we have Monday 15/22. And during the Golden Week, please be careful. The replacement day for our real lecture day is May 7. It's a Tuesday. And then May 13, 2027 are the usual Mondays. So please be careful about that. Then next point for those who are on Zoom. So there is Dhruv, Yangsan, and Irfandi. So please put into the chat your attendance. So I would. So please put your student number as shown here on the slide and your name. I'm waiting now. So if you're actually listening and you can hear me, then please put your, okay. I got, yeah, Irfandi. So please put into the chat your student name and student number and name. Please send a chat message. Okay, before the end of the lecture, please send the chat message. So click on the chat button in Zoom. Okay, very good. Thank you. So that way I can count everybody's presence. Okay, so this, and you can ask questions basically anytime if you want to, or you can ask after the lecture. So first of all, this will be a kind of a materials-oriented lecture. So because the backgrounds of people are very broad. So who has physics background here? 1, 2, 3, 4, 5, about 6, 7, 8. Who is chemistry? 2. And who is from material side? Also 2 or 3. Okay. So we have people from different backgrounds, and that means that you have looked at different aspects in your undergraduate study periods. And therefore, I try to do these lectures in a way that is hopefully useful for all of these backgrounds. And that means that we perhaps do not go into the finer calculation details, but rather I want to explain the behavior of materials. And the group of materials that I have chosen are oxides. So there are some hints already on this slide. So why are oxide materials interesting for any of you? So can anybody say where you can find oxides around us? So maybe you don't wear much jewelry, but of course all the gemstones, right? So the big stones, sapphires, rubies, like this one is a sapphire, they're all oxides, right? But also practically in everyday applications, basically all the stones, all the rocks on the ground are essentially oxides because Earth has an oxygen atmosphere. So usually the most stable state for materials is the oxide state. So if we want to make silicon single crystals, it takes a lot of energy to split SiO2 into silicon and remove the oxygen. Other practical cases, where can you see oxides here around us? If you look around this room, where can you point with a finger where you can see oxide? Okay, what is white paint made of? There are physics background people here, right? So material is white. Why is material white? Why it's not green or black or red? So it scatters all the wavelength. It doesn't absorb any light, right? It doesn't absorb anything means it has a large band gap. It's an insulating oxide like zinc oxide or titanium dioxide. So white paint, concrete, this house building is made of oxides. So the most common compounds on Earth are of course oxides, and usually they are rather they contain things like silicon, aluminum, magnesium, iron, all the common elements, of course. And of course, very common one is sand, silicon dioxide. So it's a very wide group of materials, and there are many interesting crystal structures. And these crystal structures, we will look today why the crystal structure is important in general. Why does physics come from the structure? And of course, many interesting properties. So we will look at insulators, dielectrics, magnetic materials, ferroelectric materials, superconductors, and so on, and try to see how their properties are related to the structure. Now, oxides are very broadly studied. Many of you are probably thinking what you want to do after university. So you want to work on something. So does anybody have interest in working with oxide materials in future? Anybody is interested in, let's say, semiconductor industry? Every mobile phone or tablet that you have on your tables nowadays contains probably billions of transistors. Each transistor has the critical part, of course, is the semiconductor, but to make a transistor, you need an insulating layer, so-called gate oxide. It's a very active area of study. It's extremely important materials. And without oxides, there would be no semiconductor electronics. Also, of course, every capacitor, every filter, everything in your phones is, of course, an oxide material. So I have put a very old-fashioned ceramic capacitor picture here. But there are still many open solid-state physics questions. And of course, we cannot go into the very latest things that people are really studying at the moment. But of course, high-temperature superconductivity, for example, is already known for more than 30 years, but we still don't have really a microscopic good theory of and understanding of how the superconducting state forms in these copper oxides. And there are many other interesting and emerging applications. So for example, many of the aspects of, let's say, spintronic devices, which is an interesting new area of development, often have also oxide components to them, especially in magnetic materials and such. So it's an important group of materials, and that's why it's interesting to look at the behavior of these materials. Now, we shall have 7 lectures. Today is a kind of an introduction lecture to some of the chemical aspects, structures, classifications, perhaps a little bit boring, but it's useful to introduce all of these things to everybody with different backgrounds here. Then we continue next week with looking at the electronic structure, band structure, and from that we can continue to then insulating materials, semiconducting materials, then go to metallic state, how we have a transition through semiconducting state to metallic state, and then look at metallic oxides, superconducting oxides, and then finally look at magnetic systems. And if we have time, then perhaps at the last lecture, usually I would discuss defects and perhaps some other 3-dimensional structures. So our interest is in transition metal oxides. And what are transition metals? So if we look at the periodic table, then you can see here the elements shown in green. So these are usually called the 3D transition elements. So going from scandium to zinc. So basically the transition elements commonly for oxides are titanium to copper. And if you look at the electronic structure of these elements, you see that they all have the closed shell of argon, followed by the 3d and 4s electrons. And you can see that the 3d electron number then changes. So titanium has 2, vanadium 3, chromium 5, manganese 5, iron 6, cobalt 7, nickel 8, and copper has 10. But these are now free ions. So if you have this kind of like a manganese atom freely in space, it may have this electronic configuration. We will see that how this is modified in oxides. Well, of course, especially the chemistry background people here would know that you would lose the s electrons and some of the d electrons. Oxides usually also combine other elements with the transition metals from this left-hand side. So especially these elements like manganese, calcium, strontium, barium, very common. And also sometimes some of the heavier elements here, of course, oxygen and many of the lanthanides. And in addition to 3Ds, we have, of course, the 4D elements and then the 5Ds. The big differences between them are, of course, that, okay, you know the differences, right? So let's see, which is more common in nature, iron or osmium? Who votes for osmium? More common? Nobody. Who votes for iron? Okay, one, so you won. So the 3D elements are more common, lighter elements are more common. And this is not specific to our Earth, this is common for the whole universe. I could ask you, why is iron more common than osmium, but okay, not the topic of this lecture. And of course, the abundance determines the price. So the 3D elements are, of course, more common, more cheaper. Of course, you see here these iridiums, platinums, gold, and the typical expensive elements. Of course, rhenium and such are even more so. And there are also other differences here. So the lighter elements and the heavier elements, from the physics point of view, there are important differences. So you have maybe heard about strongly correlated electron systems. We will look into what that means. But basically, the 3D orbitals are fairly confined in space. So you tend to have strong correlation effects in these lighter elements. Whereas when you go to these heavier elements, you have much larger number of electrons in the system. And this means that you have strong relativistic effects such as spin-orbit coupling. So you would have strong spin-orbit coupling systems, especially here. Very famous ones are like tungsten, iridium, platinum, so on. And then you have these lighter elements with very weak spin-orbit coupling, but strong correlation effects. So these are the interests why you might sometimes use 5D elements and sometimes you might be more interested in the 3D elements. All right. So what type of compounds shall we look at? And there are essentially, you could start from a very simple picture of just looking at how many elements you have. So first are the most simplest cases. So we have binary oxides. So binary oxides, binary means 2. So you have 2 elements. You have one metal and one oxygen. So you have things like TiO2, titanium dioxide. This is the white paint on the wall. You have Fe3O4 or magnetite. This is the oldest magnetic material known to man. You have nickel oxide, which is one of the interesting Mott insulator systems, which was triggering much of the research into solid state physics in the first place in about 100 years ago. You have osmium oxide, which is kind of unusual because it's liquid at room temperature. You have wüstite, iron oxide, which is, of course, the key to making steel. And you have rhenium oxide, which is a rare metallic oxide, very good metal. So already in this simple group, we have insulating systems like titanium dioxide. We have interesting magnetic oxides. And we have also semiconducting systems and good metals. Then we look at structurally a little bit more complex cases, which are ternaries. And actually, these are, from a physics point of view, perhaps the most interesting group. So we have here a picture of titanium dioxide rutile structure, and you have a ternary compound like lanthanum nickelate. So you have the lanthanum here in the middle, you have the nickel atoms, these gray ones in the corners of the cube, and then the red ones are the oxygens. The most important ones that we look at are strontium titanate. We look also at lead titanate and perhaps a few others. But then there are complex oxides. So things like yttrium barium 2 copper 307 or thallium 2 barium 2 calcium 2 copper 3010. So these, as you can see, may contain 4 or even more metal atoms. The structure of yttrium barium copper oxide is here. This is the famous high temperature superconducting oxide with a critical temperature of about 91 Kelvin. So it's superconducting above the liquid nitrogen boiling point. And the other one here is also a superconductor, in this case, a thallium-based compound with a critical temperature that's even higher, about 130 Kelvin. So we will look at these compounds in the superconductivity lecture. So we have binaries, ternaries, so means 3 elements. And then basically people don't count anymore. So it's like 1, 2, 3, many, and just call them complex oxides. So what makes oxides interesting from an electronic point of view? So especially those who come from physics background, of course, are familiar with looking at the electronic structure of materials. And if we think about what is so special about oxides, so first let's remind ourselves of a simple picture where the band structure comes from. So this can be looked in 2 different ways. So either we can look at electrons which are, well, let's say electrons which are subjected to a periodic modulation of the potential energy. In other words, the atomic core levels. So the difference actually comes from the difference between an amorphous material where atoms are randomly positioned and then a crystal where space is now discrete. In other words, we have a lattice of atoms. And of course, you are familiar with the textbook picture that this leads to a classic parabolic band picture, a dispersion relation. So here you have the lattice momentum K and the energy on the vertical axis, and you have these different bands forming. And in a reduced folded Brillouin zone picture, then you would have band 1, 2, and 3, and so on. So for the same momentum vector, we can have several different energies, and these are then indexed by the characteristics of the bands. Okay, this is what you are probably all familiar with, regardless of which background you come from. But how do we get from this picture to things that are perhaps insulating, perhaps magnetic, perhaps semiconducting, perhaps metallic, perhaps superconducting? So the kind of first question is what makes the difference between insulator and metal, right? So the typical picture that you would see is that if you have a single band, we have this so-called dispersion relation. And in this band, if we have electrons that fill up part of the band, let's say we are close to half filling, in that case, you can have excitations of the momentum of the electrons. So you can have a little bit more electrons on this side than you have on the negative side. This would correspond to electric current flowing through the sample. So you would have more electrons going this way than the number of electrons going that way. So this system would be metallic normally. If we look at the multiple bands, so we can have a picture where, let's say, one band is completely filled, and then the next band is completely empty. And we have between them some kind of an energy gap, which is called the semiconductor gap or the insulating gap of a material. Now, this is the usual picture of a free electron picture, where electrons do not interact with each other. Electrons only interact with the periodic background potential of the atoms in the crystal lattice. And the typical shape, this kind of a cosine type shape, comes from the so-called tight binding approximation, which basically is a multiplication of cosines of the momentum vector or momentum value multiplied by t. So what is this t here? This t, as you see, is just an amplitude of the cosine. So it's this width of this band, right? It's 2t. And well, you can have plus minus sign, so actually 4t. But now if we think about, okay, so what can be different in different materials? Of course, this parameter t is somehow determined by the structure of the crystal. So we can understand that the bands can have different widths. So bands can be narrower or broader. But just if you make the bands narrower or you make them broader, this does not give you an insulating state or a metallic state. Because regardless of how broad or wide this band is, this same picture still applies. So if you have a partially filled band, you can have excitations here which are different on the plus side and minus side. In other words, you can carry current. You can have more electrons going one direction than the other direction. So where does insulating behavior then kind of come from in oxide systems? So let's think about the kind of a chemistry picture or molecular picture of what happens when we make an oxide material. Let's say we make something like titanium dioxide. Okay, so here I write the electronic structure, first of all, of titanium. So we start from the so-called core levels or core electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p6. And then, as I showed in this periodic table picture, here comes this 3d24s2. So these are the last 4 electrons of the electronic structure of titanium. Now the titanium nucleus holds on to these core level electrons very tightly. You have to give these electrons a lot of energy to pull them out from the atom. But these valence electrons, especially the s electrons, can be removed very easily. Titanium gives them away very freely. So if we combine titanium with oxygen, oxygen is kind of hungry for another 2 electrons here to fill up the 2p6 level. So the 2 oxygens will take 2 electrons each. And in that case, these valence electrons would be removed from titanium. And we now have only closed shells. So 3p6 is completely filled. 3d electrons are gone, 4s electrons are gone. So we are in this picture. And this makes titanium dioxide an insulator because we removed all the valence electrons. But what is special about this? So 4s electrons are kind of don't care electrons. They go away easily. But 3d electrons are the critical ones that we are interested in. Again, if you look at the periodic table, you can see that the difference between these elements is basically the number of d electrons that they have. And of course, you can understand that things like titanium oxide is very different from copper oxide. So this one can go superconducting. Well, this one can go superconducting too. But obviously, it's different from, let's say, cobalt or iron or manganese. So it's the d electrons that determine basically the properties. So what is so special about those d electrons? So d electrons are neither core electrons. They are not tightly bound to the atom, but they are not completely free electrons like s electrons, which can easily be removed. So they're somewhere in between there. Now, what happens generally, remind yourself, what happens if you have just 2 electrons? The simplest system of an isolated electron in everyday world would be a hydrogen atom. So you can have hydrogen atom in your laboratory environment. In this case, hydrogen atom would have 1 electron each. So they would have 1 hydrogen atom here and another hydrogen atom here. You would have the electronic state of 1s1. So you would have 1 electron in the s state. Now, what happens if you take these 2 hydrogen atoms and you bring them close together? What do we get? We get the hydrogen molecule, an H2, right? Hydrogen molecule now has 2 hybridized orbitals because the electron is now shared between the 2 atoms. So the electron is no longer, 1 electron is no longer localized around 1 proton and the other one around the other proton, but rather the electron can be on either side of the molecule. So we have now 2 hybridized states. We have 2 electrons, so we still have 2 states. And we have a bonding state, which electron distribution in space would look something like that, electron probability, something like this. This is the bonding state or bonding orbital, and then we have the anti-bonding orbital. These are the two compound states when you bring two electrons close together. And on an energy scale, you would have this bonding orbital here now with the spins up and down on the same energy level and the empty anti-bonding orbital. So important thing to remember here is which system has lower energy. If you have two hydrogen atoms separated, or you have one H2 hydrogen molecule, which energy is lower? Let's have another vote. Two hydrogen atoms is lower energy state, or hydrogen molecule is lower energy state. Who votes for molecule is lower? Two. Do we have anybody? Three. Do we have anybody voting for separate hydrogens? One. Okay. What happens generally? The normal form of hydrogen gas is H2. In nature, H atom only exists if you break H2 molecule. You can do that, for example, if you take a hot wire, heat it up, take the hydrogen to high temperature, it will dissociate into hydrogen atoms. This is a higher energy state. So what you are seeing here is basically an energy scale. The vertical direction here is energy. By bringing the two atoms together, by making the hybridized state energy is lower. So that comes from the difference in the kinetic energy, basically, of the electrons. Lowering bonding orbital lowers the total energy of the system. And now the same thing happens when you go to not just a molecule of two atoms, but you go to a crystal, which is basically, you could think of a very large molecule. So in this picture, we would now have, let's say we look at the single atom here on the left-hand side. So here the red line would be the potential created by the charged nucleus of the atom. And now we have one electron there, and that electron occupies some energy state. So this is a classical picture of electron in a potential well. This creates, you can solve the Schrödinger equation, you get the energy level for the electron, and this is an exact value. Now what happens when you bring these two atoms close together? So let's say we are looking at two neighboring atoms in the crystal. Now we have the same thing that we have in the hydrogen molecule. In other words, we can have a case where the electron is not completely free to move. If the electron is completely free to move, then its energy level would be somewhere here above these red lines. That would be something like an s electron in a metallic system. It can go anywhere. But if we look at the d electron case, the d electron is not completely free to move. However, the d electron can hop to the neighboring site, to the neighboring atom. So there is some probability for the electron to move between two sites. It's not completely free to move, but it's not completely blocked either. This now creates the same picture that we had with the hydrogen. So the dashed line marked the original energy level of an isolated atom. Now, when we bring two atoms together, we will have again, the splitting of orbitals, the same bonding orbital and the anti-bonding orbital type picture. And the energy level will be lower when the electrons occupy these bonding orbitals. But in a crystal, if you have just two atoms, you wouldn't call it a crystal. You call a crystal when you have very large number of atoms. If you have maybe 10 atoms, you call it perhaps a cluster. But if you start to have very large numbers of atoms, basically from an atomic point of view, an infinite row of atoms, in that case, what you now have is possible hopping between different sites here. And this creates not just two new energy levels, but it creates so-called the band picture. In other words, many, many energy states within a certain width. And this is the tight binding picture case here. The width comes from here, and then the band behaviors are these kind of cosine type behaviors. So if you are familiar with the tight binding picture, so basically all you need to put into this kind of a simple kind of a toy model is basically the atomic energy level, E0. So this is the atomic state here. N is just the index of the atomic state in the chain. And then you have hopping. So you change from position. You can, at some probability, you can transfer an electron from this atom to the next atom. So you bind states N and N plus 1. Or you can jump the other direction, N plus 1 to N. So you can jump this one. And the jumping parameter is T. So the T is often called the kind of a hopping parameter. And this model is all that you need. You just have to allow hopping to the neighboring site. We don't need to allow this electron to, for example, jump somewhere here. We only need to consider jumping between neighboring sites. And this small modification to our band structure calculation model creates many important physics features. First of all, these energy states, even though they are related to the hopping between neighboring sites, basically pass through the whole crystal. In other words, the whole bulk crystal energy picture changes. It's an important feature. It says that although the interaction is local, the effect is global. The other important picture is that it creates a bandwidth with a width of, well, 2t is amplitude, or width is 4t. Another thing that it creates is this quadratic momentum dependence. So this one, close to 0k, we have basically a k-square behavior. So where does k-square come from in tight binding picture? You studied tight binding for the entrance exam, right? Yes. Why is there a k-square dependence when you are close to 0? What's the Taylor expansion of cosine? Basically, it's the first term of the Taylor expansion of cosine function. So you get the quadratic momentum dependence near 0k. And it also creates the notion of effective mass. The question is interesting whether what we see in nature, can we actually see an isolated electron? Usually we do experiments and we observe something in our experiments which we can model as an isolated electron. Now, when we have electrons in the crystal, electrons are no longer individual. As we saw, we can have this kind of jumping between atomic sites. And effectively, the material still behaves as if we have these electrons flowing through the material. And you can see these pictures where people draw dots of electrons kind of flowing as you apply voltage or pass current through a material. But in fact, the electrons are very different. These electrons are no longer individuals. They now behave as collective electrons. In other words, they have different mass. Now, electron mass normally cannot change, at least non-relativistic cases. But in a solid material, the mass behaves differently. This is somehow you could compare to human behavior. If you are alone on a track, you can run 100 meters in, well, I don't know, 9 seconds or something. If you now take a crowd and you fill the stadium with people, and all those people try to run a 100-meter dash, surely you would run much more slowly. And you could somehow keep the same model of the human, but you now give those humans a much larger weight. So if you have 1,000 people on the track, you could model it as if you have, let's say, people running who weigh on average 200 kilograms or something. So the same kind of thing happens in a solid matter. So all of this comes from this kind of a simple Hamiltonian picture. Now, the other thing, and so why oxides are important, I should mention one more time, is this notion of hopping to neighboring sites. And this is what the d electrons do in oxide materials. Not completely free, not completely localized. And this is enough to give these materials very, very rich physics. Now, there is another thing that we didn't speak about yet, which is the spin of the electron. I showed that somehow in the hydrogen molecule picture already, but let's think now about the same picture, but now let's consider that the electrons also have spin. And on average, you would have the equal number of up and down spins in your crystal. let's think of some kind of let's say an S electron system, which is half filled. So it would be this picture. S electron band, half filled. S electron band can take 2 electrons. Half filled is 1 electron. So the picture would be something like this. And we can forget about this potential picture. Let's just look at the spins in order. Now, this is a half-filled band, right? So is this a metal or an insulator? Voting time. Half-filled band with 1 electron in S state is metallic, is insulating. Everybody thinks it's metallic, and that's what people were wondering in late 1920s. Why nickel oxide? Let's look at our periodic table. Cases started with nickel oxide, but also with manganese oxide, where we have partially filled d bands. So we do not remove all these d electrons from here. These systems, and indeed something like lanthanum titanate with 1 d electron, are insulators. Why are they insulators? And the reason why they are insulators is this picture was solved by Mott, is that you have to consider the spin. So what happens now, let's say that we want to pass current through this kind of a row of atoms. It means that some electron has to move. So let's take this electron here, this number 2, and let's say that we want to move it a few sites ahead. So let's say we want to move it to this position over here. Okay, so let's look at the pictures. What happens if we do this move? We move this electron away over here. We leave a hole here, an empty site. And here we have now 2 electrons. So that's okay, because we can have opposite spins in the same orbital. We can have 2 electrons in the s orbital. That's fine. But we still have Coulomb interaction. So 2 like charges dislike each other. They want to repel each other. Coulomb interaction still applies. And this is especially true for the 3D electron systems. The d orbitals are fairly confined. So there is significant repulsion of 2 electrons. In other words, putting 2 electrons in the same orbital costs you energy. And this energy cost is usually listed as U, is the conventional letter for it. So we have to consider 2 parameters here. One is the width of this band. So this is this hopping parameter T. This determines the energy range of the band states, or the energy range here for this s orbital that we have. And now the question is whether the energy change of putting 1 more electron here, how it compares with the Coulomb repulsion, the U. If the bandwidth is very large, then the cost of putting 2 electrons on the same site doesn't matter, and we can still have a conducting system. But if we have a case where the band is fairly narrow, in that case, the on-site repulsion effect becomes significant, and the energy state, this state energy would be higher than this one. So at normal, let's say room temperature, it wouldn't happen, or let's say at some temperature. And in that case, the system basically cannot move electrons around it, and therefore it remains insulating in a kind of a Mott insulator state. So the question here is the width of the band is the critical parameter, because the Coulomb repulsion is somehow determined by the distribution of electrons. So let's say that it's the orbital size. But the width of the band is determined by how easy it is to hop from one site to the next. And oxide materials are just on this boundary. So we have the comparative results or comparative values for the on-site repulsion energy and the width of the band. And that means that we can have very rich physics, which is related to the spins of the electrons in our bands. Okay. This is somehow parameterized in the so-called Hubbard-Mott model. So what we are looking at is the hopping parameter, so the width of the band as it scales with the on-site repulsion energy. And we look at that for kind of a half-filled band. This is more common than you might expect. I mean, this, as you can see, this occurs in many systems. And if we are in this kind of a low interaction regime, then we would get the normal band picture. But once the Coulomb repulsion force is large relative to the hopping, we get to go into this kind of a Hubbard splitting where the band splits into actually two bands. One is fully occupied, one is completely empty. There's a gap between them. And this system becomes then an insulating system like a Mott insulator state. This is not a good insulator state. I mean, even a small disturbance in the structure, as we will see, will break this insulating state and will take the material back to metallic state. You can imagine that if we have here some missing atoms related to doping of the crystal, for example, then we could freely move electrons through because we would have a hole here where we can put this electron, and then you can have conductivity. So Mott insulator state is easily broken by doping. So enough of the electronic structure discussion for now. We come back to the little bit more of the details next week. But you can appreciate from the discussion up to now that you really have to look at how many d electrons we have. And this is actually, in most cases, rather simple. So let's say look at something like strontium titanium 03. This is a very nice demonstration model system. And we will look at this crystal in various contexts in these lectures. So titanium electronic structure we already looked at. It has this 3d2 4s2. And if we look at the valence states here, so oxygen is always -2, right? So strontium is always 2+, so titanium is 4+. It loses these 4 electrons from here. It has a closed shell system, so it's insulating. Now, if you would do the same thing with something like lanthanum titanate, so lanthanum is always 3+. Oxygen is still 2+, so total -6 on this side. So titanium would be 3+. Now, if you take titanium 3+, it means that we have 1 d electron left here. So now we have a d band which has 1 electron. So exactly this picture. And for the reasons that I talked about, lanthanum titanate is indeed the Mott insulator, which is easily broken by slightly doping it, for example, with oxygen vacancies or lanthanum site. We will see that in future lectures. Another important character is the oxygen stoichiometry. And usually, actually, many materials are not stoichiometric, strontium titanium 03 or some other oxide. This delta here is crucially important. Some metals more easily than others can give up their oxygen. So if you would take, for example, strontium titanate and put it into vacuum and heat it to, let's say, 700-800 degrees, the normally white material, insulator, becomes metallic. It turns black in color. And that is because it loses oxygen. So when you take oxygen away, then effectively you leave the carriers, you leave the electrons on the metal side. So you create titanium 3+. So the oxygen deficient strontium titanium 03 minus delta becomes metallic because now we have left d electrons into the titanium d orbital. And if you take this crystal and put it in air and heat it slowly to, let's say, 300-400 degrees in air, the crystal becomes white again because the oxygen went back into the crystal. You oxidized it fully. Now we are back to the ideal strontium titanate structure shown here. We are back to titanium 4+ state. We no longer have any d electrons, so the system is insulating. So oxidation state is a kind of a simple counting starting from this oxygen being -2. Then the other question is the true stoichiometry of the crystal. Important feature here is that the difference between an insulating state or a conducting state can occur for very low level, small number of electrons in the system. In other words, the strict stoichiometry question is important. So for example, if the strontium and titanium ratio is exactly 1:1 or not. Now, crystals are kind of nice in the sense that you can take often a crystal from a mixture of source materials and crystallize, grow a single crystal, and that single crystal somehow automatically forces the stoichiometric control. So you grow sapphire, you basically get aluminum 203. It's not perfect, but close to that. So we are talking about well understood phases like the perovskite strontium titanium 03. But stoichiometry can be somehow complicated, and I have a note here from previous lectures about the word stoichiometry. Stoichiometry means ratio of elements. So a material can be stoichiometric when the ratios are correct, or the material can be non-stoichiometric when the ratio is not exact. So deviates or changes from the ideal. And this deviation or doping level can be large or small, but you cannot say that stoichiometry is small or stoichiometry is large. Stoichiometry exists or doesn't exist. So be careful with the way that you use the word. So another important thing is if the compound is a single phase compound or a mixture. So for example, when we look at iron oxide, normal natural iron oxide is often a mixture actually of various oxides. And the most common ones would be Fe2O3 and Fe3O4. So Fe2O3 is hematite, Fe3O4 is magnetite. And usually in nature, they are mixed. So how do you determine which system you have? Of course, one way is to look at, for example, X-ray diffraction. Often also people use for that X-ray photoelectron spectroscopy or ESCA for kind of a chemical name for the same technique, and for composition analysis. So we would need to look at understand what is the actual structure of the material to estimate what is the number of d electrons on the iron site, because it would be different. The other question is if the material is electronically homogeneous. For example, if you have contacts between materials, usually the contact boundaries are not homogeneous. So let's say that when you do some kind of electronic device and you want to understand how the oxide works in a memory device, then you have to consider electronic inhomogeneity. Then we have kind of intrinsic non-stoichiometry. I show an example of a couple of phases here, just to give you an idea. These are so-called tungsten bronzes. So you see the basic structure of the material is tungsten O3, but the so-called A site of the structure, or the lithium or sodium or copper, can have an X here. So the crystal structure can freely vary the X over fairly broad ranges, like from 0.3 to 0.6 or so. And these structures are different. The lattice changes from cubic to tetragonal to orthorhombic, triclinic, and so on. And also the materials have quite different behaviors, can be even superconducting. And in some cases, you can have this kind of variable stoichiometries, or you can have line phases like potassium 0.3 or potassium 0.33. These are distinct crystals with distinct structure or distinct properties, kind of so-called line phases. So there can be intrinsic stoichiometry in some systems. At this point, I would like to introduce one crystal structure, which is the basis of many of the materials that we talk about. This is rhenium oxide. It's a kind of an unusual metallic oxide. We will look at its electronic structure next week. But I would like to remind here the structure. So you start with a cube, and you can see on the corners of the cube are the red rhenium atoms. And always between two metals, there is an oxygen. So this is one way of drawing this crystal. And the other way of drawing this crystal is to put the rhenium atom in the middle, and then you look at the oxygens around. And the shape that you can take this one as the unit cell. So in that case, the unit cell center would look like this. You would have the rhenium here and the oxygens on the faces of the cube. This structure here surrounding the rhenium is called an octahedron or Hachimentai. So it has 8 faces, 1, 2, 3, 4, and on the bottom side another 4. So octa means 8, so 8-faced structure. And often when we look at the relatively complex oxide structures, so one way is to draw them in this kind of a frame picture. The other type of drawing is to show the structure of these octahedral coordinations. And we know that there is a metal in the center of this kind of an octahedron. And that's why this picture is still kind of hard to see what we are looking at. So often this kind of crystal structure is just drawn like this. So you understand from this that at the corners, there are oxygen atoms. And in the center of this structure, there would be a metal atom, in this case, rhenium. So this is a kind of a very common way of drawing these oxide structures. So when you think of them, remember the corners have oxygens, just like here, these blue ones. And then in the center, there would be a metal atom like the rhenium in this picture. There are very much more complex structures like the yttrium barium copper oxide, the superconducting phase. And this is now important to think about the oxygen. I showed this structure to somehow for the YBCO structure not to be so shocking. So this is the starting point, but basically you can see the same kind of cubic structures here. So you can see the kind of cube-shaped structures which repeat 3 times in this structure. So this is basically 3 times larger in the z-axis or vertical direction. But for the superconductivity, the important things in this crystal structure are the layers, individual layers. You see the top one here. So we have here kind of copper and oxygen, but there are oxygens missing from here and from here. So the coppers and oxygens make this kind of chains along one direction. Then you have the copper oxygen layers over here. And here you can see that in addition to the coppers, you have all the oxygens are in place. So we have this kind of copper oxygen, copper O2 plane layer. And another layer is over here. It's drawn over here. And then at the bottom, you have another layer of copper oxygen chains. So going in one direction. I show here the distances. They are slightly different. So you can see in the this distance is 3.83 angstrom. The other direction is 3.88 angstrom. So it means that the A, B, and C lattice parameters are all different. So you have it's kind of an orthorhombic structure. And the important point here is that you have these missing oxygens here. Only this phase is superconducting. So how do you make this superconducting phase? Is interesting to consider the kind of oxygen stoichiometry effect. So the usual way to make this material is to take the starting compounds which contain yttrium and barium and copper, and you put these into a furnace, an oven, and you heat to high temperature. And then you let the material to react, form the crystal structure, and then you start to cool it down. And the important thing happens, what happens when you start to cool down from here? So let's say we are here at the high temperature, and now we quickly cool the material down. So we just take it out from the hot furnace. In that case, what happens is that what is shown in this plot now is temperature here. So you see we start from like 900 degrees C. And the vertical side is fractional site occupancy. What does this mean? Fractional site occupancy is defined in terms of this picture here. So the sites that we are interested in is this site here and this position here. So here the fractional occupancy would be 100%, and the occupancy of these positions is 0%. But this is not true if you cool the material quickly. If we cool the material quickly, then we can see that these two sites have a fractional, so material oxidizes, so more oxygen goes into the system. We can see the delta becomes smaller, closer to 0. Delta becomes closer to 0. Delta is 7 minus delta here. And then we have kind of uniform distribution of close to 50-50 distribution. So if we put the oxygens randomly here, here, or here, distribute them randomly in this layer, then A and B axis directions would be the same because there's no difference between them. And then the material would be tetragonal. The color is green, and it's a semiconductor. It's not superconducting. Now, if you are clever, you set your furnace to cool very slowly. And originally, when making these materials, people just discovered that if they just switch their furnace off and wait slowly until it cools, then what they get is not a green material, but what they get is a black material. And you measure X-ray diffraction, and A and B axis directions are different, so it's orthorhombic, and it's superconducting. And if you do careful oxygen location analysis, for example, by neutron diffraction, then what is apparent is that if you cool very, very slowly from high temperature, then at around 700 degrees, the crystal starts to change, and the fractional occupancy at the A-axis site goes down to 0. So the A-axis sites are these. And the occupancy of the B-axis site, so 0, half, 0, this occupancy goes close to 1. In other words, all the oxygens nicely line up in this kind of rows, and you get from a semiconductor to a orthorhombic structure superconductor. So first of all, it tells you that oxygen can be a critically important part of the oxide material because it changes the crystal symmetry, it changes also the number of electrons in the system, so it dopes. And another interesting thing about this phase is that if we start to look at we start to think, okay, so electronic structure, we already talked. You look at the valence states, you look at how many d electrons you have on the metal, then we can start to guess about properties. Well, how would this work in case of YBCO? So oxygens, we have 7. So oxygen is -2, right? So it gives you -14. Yttrium is always +3. Barium is always +4. So the only variable transition element here is copper. So this leaves copper with +7. But there are 3 of them. 7 divided by 3 gives you a copper valence of 2.33. Chemistry background people, which copper oxides exist in the world? So there's copper 2O, copper 1 plus, and there is copper O, copper 2 plus. Copper doesn't normally exist in states where the valence is higher than 2. So it almost immediately tells you that there is something interesting going on in the electronic structure here. And basically the simple ionic picture doesn't work in this material. In other words, the electron distribution between elements is different from a simple ionic prediction. We will look at that again later when we come to superconductors. So from a kind of a chemist point of view, the oxidation state is a kind of, as I say here, is a formal ionic charge, right? So what I was signing this -2s and +3s and so on. And this is mostly true if we have a purely ionic case. So we can start by giving -2 to oxygen, and then let's say in titanium dioxide, we would know that titanium is +4. And this works also for something like lanthanum ferrite. So we get, or lithium niobate. We would find that lithium is 1 plus, niobium would be 5 plus state. Iron here would be 3 plus state, and so on. But things get also complicated, not only in this kind of copper oxides, as I showed, but also something like iron titanate, because in that case, we can have 3,3 or 2,4 combinations, because we have now 2 transition elements in the compound. And the way to solve which state is lower energy, in other words, which one actually appears, it's possible to do, for example, X-ray photoelectron spectroscopy, XPS, to determine the valence states of titanium and iron. Okay, so let me see where we are. So here is a kind of a summary of valence states that normally appear. This is a list of 3D elements, 4D elements, and 5Ds. So you can see the 3D element series from titanium to copper, and then 4Ds from zirconium to silver, and 5Ds from hafnium to gold. And what is shown in these lines, you see here at the top is n equals 0, 1, 2, 3, up to 10. So 5D levels, 10D electrons. And 4Ds also, the n is the number of D electrons, and for the 5Ds. And these Bs and Ts, which are shown here, these refer to kind of well-known binary compounds. So for example, 4+ state for titanium dioxide is a binary oxide. So we can have that one, and we can have also titanium oxide would be here, N would be 0. Other binary oxides also exists where it can have valence states can vary here. Normally you see there is a kind of a pyramid shape here. So if you are close to the left or right hand edge of the periodic table, then you have either here you have few electrons, or here you have few empty states. So the valence state variations can be small, and always the valence state variations are high in the middle. So interesting cases for high valence states are like chromium, manganese, iron, cobalt, and so on. Cobalt less so, chromium, manganese, iron. So we can have, for example, things like hexavalent chromium compounds and so on. In case of iron, often iron tends to not to go to this very high valence state. It tries to go to some kind of cluster states. And the interesting thing is that for some of the 4Ds and 5Ds, not all D occupancies exist. So some like D7 or D9 states are missing for these heavier elements. And finally, there are cases where this kind of valence state calculation counting doesn't give you the right result because of so-called peroxides, where you have kind of an oxygen 2 molecule 2- state. Famous case is, for example, strontium O2. So if you want to synthesize some oxides, you would contain strontium, you might take strontium oxide. But actually, the most stable form of strontium oxide is actually strontium O2, a peroxide. And in some other cases, like potassium 3 chromium 08, a well-known compound, but actually, if you would look at the start counting from here, so 8 oxygens would give you -16, -3 would give you a chromium 13 state, which is obviously impossible because there are enough D electrons to remove from it. So instead, there are actually chromium would be in a 5+ state, and again, you have this kind of a molecular oxygen state in the crystal. And we already mentioned this high TC superconductors where this doesn't work because you would end up with like copper 2.6 or copper 3+ or something. So basically, some of the charge lives on the oxygen side. So oxygen is not exactly 2- in these compounds. Then we come to another aspect, which is mixed valence. And mixed valence is actually quite important feature, which has slightly different meaning depending on how you look at your material. So if we look at something like magnetite, Fe3O4, so we can see that the iron's average oxidation state would be 2.67. But actually, what we see is that it's a mixture of iron 3+ states and then effectively iron 2.5+. This transition happens at the 120 K, so-called Verwey charge ordering transition. So there is actually a distribution of Fe2+ and Fe3+ states in the material. We will look at that when we look at the spinel structure. So can we talk about the kind of a well-defined valence states, like let's say one iron here is 2+ state and the other one is in 3+ state? Or do we have a mixed valence state, which is something like 2.5? So what's the difference? And actually, the question is basically about the so that if you have a mixture of 2+ and 3+ states, in principle, it's possible that an electron would be transferred from one ion to the other one, right? And then it's a question of how quickly the electron hopping between several sites. So how quickly the electron is moving between different sites. So depending on how you measure your material, you may see an average valence state, or you may see a mixture of two valence states. So this is a similar picture to, let's say, you are taking a photo of a race car driving by, right? So if you take a normal picture, the car is kind of blurred as it moves across your picture. So you don't get the sharp picture of it. So you could say that the car is kind of distributed in positions. But if you have a flash on your camera, so you take a picture and there is a flash, and you make the exposure very short, so your camera is very fast, then you see a car exactly here or here or here. And the same thing happens in measurements. So for example, this is, I think, useful to know because people here probably are using different techniques in different labs. So you always have to think about, what am I seeing with the measurement technique that I'm using? So if we look at something like X-ray photoelectron spectroscopy, so this measures the escape of core electrons from the material. The electron excitation from an atom is basically an instantaneous process. So it happens on time scales probably faster than femtosecond, somewhere on that scale. So the characteristic frequency is about 10 to 16 hertz. So it gives you a kind of, it's like a flash photography. It's an instantaneous view of the material. But there are also much more slower methods, like maybe not so familiar to you would be mass power spectroscopy, which is often used for analyzing, let's say, iron compounds. So there the probing is much slower, 10 to 7, so let's say below gigahertz. If we look at very common techniques for looking at valence states in materials, you would use electron paramagnetic resonance. This is gigahertz range frequency measurement, or NMR, which would be a kind of precession rates are typically hundreds of megahertz. Hyperfine interactions can be much more slower, like kilohertz range. NQR about same range. And of course, when you look at things like electrical conductivity, it's basically a DC measurement. So it's a zero frequency measurement. That is also true for magnetic susceptibility measurement. So you go to SQUID, for example, or if you measure specific heat. These are all low frequency measurements. So here you would see the average valence. So if you would measure something like this type of an oxide, you would see that effectively material behaves as if you would have Fe 2.5. So you would have 2.5 electrons removed from the iron. Whereas if you would use photoelectron spectroscopy, you might see actually two different peak positions. So, and you could say that, okay, here is iron 3 plus and here is iron 2 plus. So it depends on which technique you use and how quickly this kind of a hopping of the electron from one side to the other happens in the material. So you have to be a little bit careful, because if you try to characterize an unknown material, you have to always consider what is the rate of the measurement that you are using. Okay, another important background issue that we have to mention is thermodynamic stability. So what's your, let me ask you for a moment. So what's your understanding of what happens if you, let's say, take an oxide material at some given environment, oxygen pressure, and you heat? So let's say you take something like iron oxide. So you take magnetite, what we showed here, this magnetite here, and you want to make iron. So you want to make some tools or something. How can you take iron oxide and make it into iron metal? How would you do that? So Iron Age started. I'm not sure about Asia, but Europe, started somewhere in Mediterranean area, Rome and Greece and these countries. And if you go there now, the islands in the Mediterranean are all empty. There are no forests. They burned all their trees, making iron, basically. So you heat. You heat at low oxygen pressure. You don't have vacuum pumps in Iron Age. So the way that you steal the oxygen is you put in carbon. So you mix with charcoal, you burn, you blow to high temperature, over 1,000 degrees. Effectively, the carbon is eating away the oxygen, so you are left with iron metal. High temperature, you get the metal. You keep in air at low temperature, you oxidize to oxide. Is the stable state. Works for iron, works for nickel, but doesn't work for all elements. Let's come back to that in just a moment. So the stability of a reaction is basically, let's look at some method, or formula. So usually in a textbook you see this Gibbs free energy. So you have enthalpy and entropy change. Okay. So we are looking at the reaction where you remove some of the oxygen from the metal oxide. So we have some metal oxide here, like TiO2, and let's say we want to remove one oxygen, go to TiO and remove half a mole of oxygen. So enthalpy change is not major here. Entropy change mostly because of the oxygen gas evolution. So entropy change brings you logarithm of oxygen pressure. And if you put the gas constant in it, then usually you would end up with something like this. So the equilibrium of this reaction, this is a constant. So you have temperature here and you have a logarithm of pressure. So this gives you, it tells you that the oxygen pressure, logarithm of oxygen pressure is related to the inverse of the temperature. And this can be plotted in what is known as an Ellingham diagram. This is a complex diagram, so let me walk you through this. So here is the 0 point, is on the upper left-hand corner. And then what you have here at the bottom on the x-axis is temperature. And you see this is Kelvin. So 1000 degrees C is somewhere around here. Middle of this plot is 1000 degrees C. And then here are the free energy differences. We can forget about that. But the graphs or the scales which go across the edges here is oxygen pressure. You see here is oxygen pressure, PO2, atmosphere. I have to put down glasses here. Okay. So here we have atmospheric pressure. Here is 10 to minus 2, so 1% of atmospheric pressure. Here is 10 to minus 6, so kind of mechanical pump vacuum. So if you have an oil pump, then you get this level of pressure. So if you have turbomolecular pumps, cryopumps, you get to about this level of pressure here, 10 to minus, let's say 10 to minus 10 torr, so 10 to minus 13 atmospheres. So you get around here. Then if you go to, this is about the same level of vacuum if you go to the space station. And then if you go out of the solar system into some intergalactic space, you can get somewhere around here. But actually in laboratory, you don't have to make oxygen pressure by pumping vacuum. It's easier to actually reach these very low pressures by mixing carbon monoxide and carbon dioxide. It gives you a balance of oxygen. Or you can mix hydrogen and water, also gives you a balance of oxygen. So this is technically how this is done. You can go to very low partial oxygen pressures. And then you take from here a line. Let's say that we are at 10 to minus 6 atmosphere pressure. And you draw a line here from 0 point to this pressure line. And now you can have temperature on the bottom. So you see here is a line for nickel oxide thermodynamic equilibrium balance. So at this crossing point here, if we are on this side of the line, we get nickel oxide. And if we are on this side of the line, we get nickel. In other words, if we are at 10 to minus 6 atmospheres, if we heat the system above 1600 Kelvin, So about 1,300 degrees, then nickel would reduce back to a metal. And if we are below 1,300 degrees C, then we would oxidize to nickel oxide. Another thermodynamic, so the lines end here because of melting. So material melts, then the line ends. For copper, you see here is a copper metal, copper 2O and copper O. So oxidizing copper, they are quite close. Manganese is somewhere here, melts at very low temperature. Gallium oxide, gallium to gallium oxide is here. Manganese goes through valence states here from metal to oxides. But then there is this guy, this one, sapphire, aluminum oxide. And you see where the balance line is. So to reduce aluminum to aluminum metal at kind of, let's say, reasonable temperatures. So we are somewhere 1,300-400 degrees. So let's say somewhere here, we would end up, crossing point would be here. So if we draw the line from here, we would end up at oxygen partial pressures of like 10 to minus 20 atmospheres. Completely impossible in a kind of practical sense. So how is, you all use aluminum cans for drinking, use aluminum in all of the places. How is aluminum made? There are a couple of materials people here. How do you go from aluminum oxides, so bauxite, so aluminum raw material? How do you go to aluminum metal? You cannot do it the same way as iron. I mean, in iron, you just take charcoal and magnetite, you make a huge fire and kind of put clay around it so air doesn't go in too much. And iron melts and flows out from your furnace. How do you make aluminum? You use it every day. How is it made? Okay, the other thing you use every day is silicon. How do you make silicon from sand? So in case of silicon, you take carbon rods, you put them in the sand, and then you pass huge amount of electric current through it, heat, and the oxygen loves carbon more than silicon because carbon dioxide is even more stable. So all the carbon says bye-bye to silicon, goes to or the oxygen says bye-bye to silicon, goes to carbon, and you are left with silicon. Basically, the same thing happens with aluminum. So you do electrolysis in a salt. In a salt solution at high temperature, you do electrolysis, huge amount of electricity to produce aluminum. So producing aluminum is extremely unfriendly for nature. That's why we have to recycle it. So aluminum is a tricky guy here. And you can see the reason in the thermodynamic stability Ellingham diagram plot. So iron case is kind of, and aluminum is kind of fixed. So you see there is only one 3+ state. There is no such thing as aluminum 1+, 2+. Just goes aluminum metal to 2O3 basically. Other systems are kind of, so iron is somehow simpler, but somehow much more complex. So aluminum case, you only have this aluminum 203 or aluminum. So you have only two choices. Iron case, it's very flexible, right? So iron is in the middle of the 3D series. So you are in the middle of the series, you have lots of possible valence states. So we can have iron oxide or wüstite. We can have iron 304 or magnetite. We can have iron 203 hematite. So how many oxygen atoms per iron? Okay, FeO wüstite 1:1. Fe3O4 so has higher amount of oxygen, and the highest amount, 1.5 oxygens per iron, would be in hematite. So this is the most stable oxide phase. But you can see as you go across the oxygen content in this material and the temperatures, you can see the different liquid phases, solid phases. So you can have wüstite phases, wüstite, magnetite. Magnetite is a kind of a line phase, which actually spreads out at high temperature. So probably somewhere deep underground at high temperature, high pressure, magnetite forms easily. And otherwise hematite forms at high oxygen contents. So we have to consider these many phases that can appear in the phase diagram of the material. So in case of iron, actually getting phase pure materials can be very difficult. So if you want to buy, for example, a pure magnetite crystal, you have to pay lots of money for that. So then we have to think a little bit about the microscopic structure of materials. This is critical for understanding crystal field splittings and electronic structures. So I give a couple of comments today here. So what is shown here are, again, 3 rows. So we have the 3Ds from scandium to zinc. We have the 4Ds from yttrium to silver, and then the lanthanides and the noble metal series here. And what is shown here for each element are the most common oxidation states and coordinations. So what is a coordination? Let me show you briefly next page. So coordination says that if you have a metal in the middle and then you have oxygens around it, you can see that the oxygens can take on different shapes. So there can be kind of planar coordinations, tetrahedral, octahedral, and so on. And this symmetry difference is shown here. So the most common ones, you see, the shapes triangle would be a tetrahedral coordination. So we would have 4 oxygens around a metal site. Then square planar case, where we have a metal in the middle and 4 oxygens around it, or an octahedral case, where we have metal in the middle, oxygen top, bottom, left, right, back, and front. So this is the octahedra that I showed to you already in case of rhenium oxide. And then higher coordinations of more than 6. And you can see that there are some general variations. So of course, as you go across the transition metal series, the ionic radius decreases as you kind of remove electrons. And generally, you go to kind of ionic radius variations. Well, of course, you can have larger ionic radius here for the 3Ds, 4Ds, 5Ds kind of go down here. And generally, smaller ions, so you can see the octahedral coordinations, the 6 hexagons here. This is the most common everywhere. And relatively rare cases like palladium oxide, there are these square planar cases over here. And then a few, very few tetrahedral cases, again, for the left-hand side of the periodic table. And a few tetrahedral cases are possible for like vanadium, chromium, manganese, and in the middle of the transition rows. So these coordination kind of observations are written on the slide here, so you can think through these, what these means. But basically it says that small ions would go to tetrahedral sites. Most ions go to the octahedral sites, and very large ions may have larger coordinations. So for example, you can see here as the ionic radius becomes very large, then you can have larger coordination cases. These are quite rare. So that's why mostly we are looking at these octahedral and some tetrahedral coordinations. So what do they look like? What do the words mean? Here is a square planar coordination. So it means that you have metal, and on the same plane, you have 4 oxygens. This structure here is a tetrahedron. So tetrahedron has 4 faces, 2 like this and 2 like that. This is shown here. And actually, the tetrahedral coordination is very common for some of the oxides. You can see it in a cubic structure here. So you have 2 oxygens along one diagonal and 2 oxygens on the bottom diagonal. The most common bonding type is this one, which is the octahedral case. So you have 6 oxygens around the metal site. And this actually is, we will look at a number of details of these type of systems, because there are very, very important distortions in some of these. So for example, when you go to ferroelectric or piezoelectric materials, we often have metal offsets from the center of the octahedron. So some bonds become significantly shorter than the other bonds. Why this is important is that you remember that the effective charge carried by the oxygens is negative. The effective charge carried by the metal ion is positive. So if you have this kind of a distortion in the crystal, it means that you have now a kind of a dipole. So your positive and negative charges on average are shifted from each other. So this would be a polar crystal or perhaps a ferroelectric crystal. The other very important feature is so-called Jahn-Teller distortion. In other words, this octahedron can be stretched in one direction, made taller, or compressed in the same direction, made shorter. This significantly changes the crystal field experienced by the metal. We will see how it influences the electronic structure. So I just introduced to you basically the words here. Now, the most common crystal structures that we will see for simple oxides, you may see kind of rock salt structures, which is illustrated here. So cubic structure where you have metal and oxygen always neighboring to each other. Very much more complex structure. It's difficult to project, so this actually doesn't tell you much. You would have to look at the 3D projection of corundum, which is shown here. So this is a typical for these metal 203 type materials like aluminum oxide, which I showed you, this sapphire crystal here, but also titanium 203 and some other structures. Then there is the rutile structure, so titanium dioxide, which is shown here. And the starting point of perovskite structures, or this cubic structure, which was this rhenium trioxide. That one we already looked at. So here in this structure, you can see these 6 atoms around the rhenium site. So 6 oxygens around it. So you have this octahedral coordination here. Where else do you see an octahedral coordination? In the rock salt. Here is the metal, oxygen bottom top, front back, left right. Well, what about the rutile structure? Metal is here in the middle, oxygen front back, up down, and the other direction up down. Again, basically this is the same coordination that you see here. So in many different crystal structures, you still have the basic coordination shape of the metal ion is the same or similar. So as I told you, so for rhenium oxide, we can show the atomic positions, but actually it's often useful to think about these coordination shapes because it's easier to draw the crystals. And you can see here the kind of a 3D picture and then reduced to this kind of an octahedral view of the rhenium oxide plot. So this would be rhenium oxide, but you can draw the rutile in exactly the same way, because in rutile you have this octahedron here, it's just tilted. So if you draw these, you can see that the lattice consists of a number of octahedra which connect either at corners. So these are corner sharing. So corner sharing means that the same corner is shared by 2 octahedra. In rutile, you get edge sharing. So 2 oxygen atoms are shared between neighboring titanium sites. And then finally, in corundum, you have face sharing. In other words, 3 atoms are shared between 2 aluminums. So the faces are touching. More complex structures then go from binary systems to ternary systems, where you have one additional atom in the system. And if you have one additional atom in the system, then we can have things like the perovskite structure. So for example, we would have titaniums in the corners and strontium in the middle, or a layered perovskite like potassium nickel fluoride structure, where we would have the potassium atoms between layers of octahedra. And then more complex cases where you have a combination of octahedral coordinations and tetrahedral coordinations. This would appear in, for example, spinel structures. And most of them are actually usually distorted. So these complex structures like spinels actually look like this. So here you can see the tetrahedra are these green ones. And then in between, if you look at the blue atoms, you can see that they have neighbors up, down, left, right, back, front. So these are the octahedral coordinations over there. This is, for example, magnesium aluminate, but also typical spinel structure is magnetite. And I will show you more detail of magnetite structure later on when we look at the magnetism. Other important materials are garnets. Garnets are silicon, for example, calcium 3, aluminum 2, silicon 3O12. And very important material is yttrium iron garnet, or YIG, yttrium 3 iron 3O12. This is very important material because it's an insulating magnet. So usually magnetic systems require spins, right? Unpaired spins. So if you have unpaired spins, then it means that it looks like you have a fractionally filled band, because in a filled band, you have equal number of up-down spins, so no magnetism. So if you have ferromagnetic behavior, you should have unpaired spins, so it should be conducting. YIG is an interesting magnetic insulator, and it's a very, very important material for microwave electronics because you can have magnets with low loss for microwaves. Another important material is YAG, yttrium 3 aluminum 5O12. YAG is basically a transparent crystal that is used to build lasers. So typical lasers are glass lasers, are neodymium YAG lasers. Maybe some of you are working with them. So very high power lasers for used in industry and research are YAG based lasers. So garnet structure is quite complex. It has many layers. And if you draw the different layers, you can see the coordinations, what the YAG crystal looks like. And finally, I would point out that many of these crystals are not ideal. In other words, we have to consider bond angles. So if you look at, for example, what I drew here, these pictures show the kind of metal, oxygen just goes in a straight line. So this gives you a bond angle. Let's say oxygen metal to next oxygen gives you a bond angle of 180 degrees. This is quite rare. In most materials, we will look at the tolerance factors later on, but what is important is that in most systems, there is an angle to the bond. So you have one metal, oxygen, and next metal. For example, you could draw like 150 degrees, 160 degrees, something like that. So what this means is that in actual crystals, often these octahedral coordinations, this shell is very stiff. It's very difficult to distort this octahedron. But octahedra can very easily tilt. And this what you see create here, this bond angle, this oxygen here in the corner, which is shared between two octahedra, this angle is about maybe 160 degrees or so. So it goes up and down and up and down. And the same thing goes down in this direction, and it also goes through the crystal in the third direction. So this would be usually leads to a reduction of the symmetry to a rhombohedral or even to monoclinic shapes. And again, it affects the band structure. Why does bond angle change band structure? Is anybody run into that? Why is bond angle important? So far, we only talked about the periodicity of the crystal. And in the very beginning of the lecture, I mentioned this guy here, the T, the hopping. And I said that, okay, hopping T can change. And if you change the T, what happens is that you change this width of the band. You tune the width of the band, right? So that is because it tells you how easy it is to hop. Bond angle is the primary thing that controls hopping. If you have a straight bond, you have exact overlap of oxygen 2p orbitals and 3d orbitals. Electron can easily hop. The band will be wide. You change the bond angle, you reduce the T, you reduce the hopping, you make this T smaller, you make the bands narrower. You make the bands narrower, you come to this guy. You now have to, you are reducing the bandwidth. You are now in a regime or in a region where the bandwidth starts to compete with the on-site Coulomb repulsion. So you will make the electron correlations. So this would be a correlated electron system. You make the correlations stronger. So if you take a material and you want to tune the correlation strength, one way that you can do is go to the high pressure lab, put your material in a press and squeeze it. This squeezing will tilt the bond angles, reducing the T, reducing the hopping, narrowing the band, and taking to a more strongly correlated electron regime. So that's why the distortions of the crystals are actually a very convenient tuning parameter for adjusting the hopping rate and the bandwidth of the material. And finally, one more comment is that unit cells can be large. We looked at the simple crystals like perovskites or some of the others, so the structures which I showed here, and you can see the unit cell would be kind of smallish. But that's not always the true. You already get the idea from garnets where the unit cell becomes very large. And then there are some crazy cases like tungsten bronzes. For example, this is rubidium-3, niobium-54, O146. This is a huge crystal unit cell, but it's very beautiful. Okay, and then of course I think we can, basically we're out of time for this week. We can stop here. So next week we can continue discussing of, well, this is just an illustration of the complexity of the unit cells of high TC superconductors. These are the mercury-based compounds. We will look at these in later lectures, so we can skip that today. But basically next week, we will continue looking at the transition from what determines the transition from insulating to conducting systems. And in particular, we will look at the kind of crystal field effects. And that's where the distortions of the crystal structure become important. So especially this effect, which I mentioned here. So this kind of Jan Teller type distortions, which stretch out the crystal symmetry and change the crystal from a cubic to a tetragonal or orthorhombic system. Okay, so time is up. So let's finish here and we continue next week. And I would be happy to take questions if you want to ask something. Now is a good chance to ask about the lecture course. If somebody has any question, what you have to do, or yeah. Uh-huh. Did we get to page 35? Maybe we did. Yeah. Okay. Yeah, it's a good question. So you see in this picture, actually, this is the tilts happen in all three directions. And this is actually a rather complex picture. It's a so-called, there is a kind of a Glaser model for it. Glaser was a person who published a nice paper on it. And you can have two choices. So if you squeeze your material in just one direction, so uniaxial pressure, then typically it stretches the other direction in a kind of a Poisson ratio picture. So in this case, normally Poisson ratio is positive, so around 0.3 or so. So normally unit cell volume more or less stays the same. So if you squeeze in one direction, you expand in the other. There are some very rare systems where Poisson ratio can be negative. So if you squeeze this way, this direction also becomes smaller. You can find this kind of a toy in toy shop. There is a kind of a circle which you can squeeze down to kind of a small toy and then stretch out as a ball. These are kind of negative Poisson ratio materials. But yes, normally uniaxial pressure leads to stretching the other way. So you would imagine that the other direction you are reducing or you are approaching 180 degrees for the bond angle. The case, if you want to avoid that, then you can do isotropic pressure. So then you apply pressure in all directions. then of course you just reduce cell volume. Then all angles become larger. But yeah, you're correct. So uniaxial case, you get two effects. So that's why high pressure physics can be quite tricky.
Hello, am I
Yep.
audible? Professor, I have a follow-up question.
So we have a
So,
question from Zoom. Yeah, please.
so does this mean that by controlling the amount of pressure I'm applying, I can actually control the bond angle and I can engineer my tip, the hopping parameter?
That is so, yes, if you apply high pressure on the material, yes, you can control the bond angles and you can change hopping parameters. Yes, that's correct. You understood correctly. Hmm. Okay, so if nothing else, then I will see you next week. And next week, please, before the lecture, please download your lecture notes. I will put them on the web page probably on Sunday. So you can download them maybe Sunday night, Monday morning. And if you want, you can print them out. Or if you use some tablet or laptop, you can use these, whichever you prefer. But generally, I will not print anymore these. So please bring your own lecture notes. And you can find everything about the lecture on the homepage, which is shown here. So this laboratory homepage, lecture TMO. You can download notes there, and you can also see the video there. Okay, thank